So yeah, we're going to talk about proof composition, which is a new feature we just released with version 0.20. And we're really excited about because it basically enables accessible recursion from modular ZK apps. We're going to basically go into detail about what that actually means and what kind of benefits it brings to developers and to users. All right, so here's the outline. We're going to talk about what is composition, and then we're going to get into how it works, why it's useful, and we're also going to dive deeper into recursion, which is kind of the underlying core technology that allows for composition. One thing to do some housekeeping, feel free to interrupt and ask a question at any time. Understanding the recursion is easy, assuming you already understand recursion. If you don't, then you might have some questions. So definitely feel free to share them. It helps everybody learn. So quick last time on Study Club, I want to talk about what is the ZK VM. So a virtual machine is a computer inlaid in software. So basically you have just like a physical computer, you have inputs, your program, and then those together run on the virtual machine to produce an output. If you want to know what a zero-knowledge virtual machine is, well, it's a virtual machine that is implemented. It's a computer that's implemented in zero-knowledge software. So basically, this is often arithmetic circuits are kind of a technique for this, but just as a general matter, you can think of this as like a different kind of execution environment, different kind of software, different kind of emulation, but this exact same purpose is there. So basically, you have your program and your inputs. They run on the ZK VM. And the output, you have the output, and additionally, you have a proof or a receipt, or a proof that is part of the receipt. And together, the proof verifies the output such that when you hand someone a receipt, they both know that they know what the output is, and they also have a proof that it was computed correctly from that program and those inputs. There's also some more terminology we use within RISC Zero. I will try to avoid using it myself, but I slipped sometimes. So basically, we refer to the ZK VM as a guest. This goes back to the VM terminology. So there's the guest and the host in the VM world, and we refer to the ZK VM sometimes as the guest. The output is sometimes referred to as the claim, as in you're publicly claiming something to be true. And the proof we sometimes call the seal, basically as if you're sealing a letter. So if you see me using those terms, kind of know that these are roughly synonymous, although there are some subtle differences, which is why we use these terms in the first place, but I'll try to avoid using them for this presentation. Just want to give a quick heads up though. So now we can talk about what is composition. So composition enables verifying receipts or proofs inside the ZK VM. And what does it actually look like when you're writing a program? So programs for RISC Zero are written in Rust, and this is a couple of lines from like an example of a ZK VM program. So here you're importing our RISC Zero SDK, and in it you have this env : verify function, and you pass in an image ID which identifies the program. So basically, go into this diagram here. The program is one of the two inputs to the ZK VM. Tell it to run. And we use the image ID to, which you could also refer to as a program ID, to identify that program for the world. And in this case, we're identifying the hello world program. And we additionally pass in what we expect the journal to be, or the output to be. And the output we expect is hello world. So basically, we're saying this verify call here is basically saying that we want to verify that there exists a receipt that attests to the fact that the hello world program outputs hello world. One thing that, if you're familiar with verifying receipts outside of the ZK VM, you might notice is that there is no full receipt here. And we'll talk a bit about why that is the case and why that allows for a more efficient design. But essentially, the kind of high level idea behind composition is it allows you to verify receipts inside the ZK VM. And the way you verify receipts inside the ZK VM is calling the env : verify function. So let's talk about why this is useful. The first use case that is kind of critical and so you can't do without composition is privacy preservation. So you might have multiple parties with their own private data. So for example, you might have a bunch of people who have their own secret keys. You might have medical records split across multiple databases. You might have, well, there's lots of cases in which basically you have multiple people or parties involved, and each of them has their own private data they do not want to share with each other. Without composition, in order to produce a proof over all this data, you have to put it all in one place and give it to all to one prover to run their computation over. In the case when with composition, you can have each individual party produce their own proofs by running the ZK VM over their own data they hold privately, and then combine all those proofs by composition to get a single proof for the whole thing. So two examples here. One is basically if you want to do publicly verifiable secret sharing. So this is useful if you want to set up a multisig or consensus network or a randomness beacon. So see all these kind of useful applied primitives in the world of decentralized computing. Often one of the key things you need is a secret sharing. And we would like to have, and often we want to have a publicly verifiable secret sharing. So in this case, what you can do is each party has their own secret key, which they definitely do not want to share with each other, because that would break the whole purpose of the whole system. And they can verify that they first broke that key into shards and then shared those shards with each other via encryption that occurs inside the ZK VM and is therefore verifiable. You can then take all those individual proofs that each individual secret sharing is correct, and then combine them by composition. So basically, with the end result of all this, so you have a single receipt, a single proof that verifies the entire publicly verifiable secret sharing to be correct. Then another example for this is you do queries over sharded private data. So as I mentioned before, you might have sharded data like medical records, for instance, split across multiple hospitals or research institutions, or just generally siloed across multiple environments, and those silos cannot mix, often by law. And if you want to run a query over the whole thing, let's say you want to know the average age of all patients who are admitted with a heart attack to hospitals across the US, let's say. There's no way to do that with one database. And so you need to actually, the hospitals involved certainly do not want to put all the medical records, give them all to one party. So instead you can produce run that query over each individual shard, and then take all those proofs, send them to a final prover, which composes them all together, and then you have the final result, which is the query over all the databases that were all sharded as if they were one. All right. So the next use case I want to talk about is proof aggregation. It's basically taking many proofs and then combining them into one for efficient batch verification. This is important in cases in which verifying all the proofs that you might have to would be otherwise too costly. So for example, you might have in your ZK VM a program that can prove an entire block of transactions. If you're running this on a blockchain, then you would end up with a proof for every block, which over the course of a year might be it'd be on the orders of tens of thousands or more individual proofs. Verifying all of those would be intensive, especially for the lightest of clients. And so we can use composition to actually aggregate all those proofs after the fact and produce a single proof for the validity of the entire chain. So that way any clients can download a single proof, verify it, and know the entire chain history is valid. Another example, this would basically be to incrementally prove a tally of ongoing votes. So say if you had a ballot box and an election was open, people could be submitting their votes and producing, let's say, a proof that they are an eligible voter, or that their vote was signed, et cetera, et cetera. And you can submit all those proof into the ballot box, and the vote operator could basically aggregate those proofs by composition to produce a single proof at any given time that the ballot box is correct, the tally is correct, that the entire election is proceeding according to the rules. And all of this basically has a single proof, and this is enabled by composition. And then kind of a third use case, which is kind of focused on developer workflows and our ability to actually build these programs, is it allows you to split your code to modules for more flexibility and maintainability. So, for example, you could, if you're writing an image processing pipeline, instead of having to include every single one of your image filters or other functionalities you want to run over the images into a single guest program, into a single zkVM program, you can instead split it into distinct modules where each one may influence a single filter or a single operation, and then run each of those filters in turn, and then combine them by composition. So basically, you get this more modular way of constructing your application, which is much more conducive to rapid development, to expanding things later on, to basically it just kind of really works well with software engineering practices. Another example of this is basically you can utilize zkVM programs written by other teams. So if you're given a program, it's already working as is, and you just want to basically use that program as part of your overall system, you can run it and then verify the receipt inside your own program, and basically and effectively communicate between these two zkVM programs without having to rewrite their work or compile it into your own application, or otherwise mess with what that other team wrote. So it provides a really nice way to basically take programs written by multiple parties and combine them in a way that supports really flexible, maintainable, powerful applications. So let's go deeper into how composition actually works. So I mentioned before, if you look at this API here, you don't see a full receipt that is in the API call. And the way that works basically is instead of verifying the receipt right away, the ZK VM essentially assumes that there is a valid receipt, that a valid receipt does exist. We record this assumption onto the receipt that we are currently producing, and what results is called a conditional receipt, or we call it conditional receipt. An example of this as an English claim would be something like, this meal is vegan, assuming none of the ingredients are animal products. And this basically is saying, if we just make this assumption, then we can say that this other statement is true, that the meal is vegan. However, we may not know yet whether the assumption is true or not. And if the assumption turns out not to be true, well, then we don't know anything about whether or not the meal is vegan. And that's, for instance. So basically, but the core of this idea is that basically you can make conditional statements and encode what assumptions you're making, and then come back later and actually prove all those assumptions to be true. And once all those assumptions have been shown to be true, then you know the overall statement is correct. So we're going to use an example here. It's a mildly silly example. I think it gets it helps get the intuition for it. Which is, let's imagine we wrote a zkVM application, which takes in a list of ingredients, takes in, and basically will say whether or not the meal that is produced by them is in fact vegan. So what we have here is what we call a receipt claim. This is the actual data structure we use to encode the output of the zkVM. It includes a number of things. So the first one, developers who have used this before will notice, is the journal. The journal is part of the output. And basically that is where people put the actual, what is kind of thought of as the main program output, what you want to record and as part of the receipt for everybody to see. There's additional important fields here, which is the pre-state, which is also in the case of execution is where the program identifier, the image ID, is set. There's also a post state. There's an exit code and input. And we won't talk about those three fields here, but just kind of this data structure as a whole is the core data structure. Basically talks about how the execution proceeded. Basically, it is the claims that are being made by the ZK VM. There's an additional field here, which we introduced with composition, which is the assumptions list. So you'll see that as part of the output, and we'll talk about how that helps us. So execution starts with no assumptions. So basically, let's imagine here we are actually building a running receipt, and at the very start of execution, we have an empty journal, we have no assumptions, and we have our program is the isVegan program, identified by isVegan ID. So we're starting execution here. And at some point, we basically want to verify that the first ingredient in our list is in fact vegan. So let's say the first ingredient is peanut butter. So what we're going to call is we're going to say is vegan, in verify is vegan ID peanut butter. And basically what you're saying is that you are making an assertion that an assumption that there does exist a receipt that verifies that peanut butter is indeed a vegan ingredient. And you can see here that basically that the assumptions list has gone from being empty to having a single entry, this 0x68AD, which is just a hash of the receipt claim below. So basically, we now on our running receipt, we have an assumption that peanut butter, that there exists a receipt showing that peanut butter is a vegan ingredient or a vegan meal. And you might think of this as this also can go recursively as well. So basically, in order to prove that peanut butter is vegan, you might need to show that peanuts and salt and palm oil maybe are all vegan as well. So see, this is one level, and you can imagine that also goes down further. This is part of the modularity. But the core here is basically that when we call mVerify, it adds one assumption to the list. So the other ingredient for our peanut butter sandwich is sourdough bread. So we're gonna call mVerify is vegan sourdough bread, and that will add a second assumption, this time to the front of the list, which encodes that it's an assumption that there exists a receipt showing that sourdough bread is vegan. So now we have two assumptions. One is that there exists a receipt that sourdough bread is vegan. So the other is that there exists a receipt that shows that peanut butter is vegan. And when proving completes, now we produce this receipt here. It says that a peanut butter sandwich is vegan, but it has two assumptions on it. And so basically, this is like the conditional statement we made before. Basically, that that this is true if these two assumptions are also valid. And so if you hand this receipt to a verifier, the verifier won't really know whether or not to accept it. They will basically they see the statement. The statement as a whole is valid, but there's two assumptions on it. And so basically they can't know, are those assumptions true or are they false? Like if the assumptions are false, then then the whole thing doesn't really say anything at all. It's kind of becomes meaningless. And so basically they don't know, the verifier does not know whether or not those assumptions are valid. So instead we need to remove those assumptions. And the way we remove assumptions is by what we call resolving them. So what you do is you take the conditional receipt, which is the one with the two assumptions on it, and then you also take a receipt that actually proves that the first assumption is indeed a valid assumption, that it is true. So you verify this conditional receipt here, you verify the receipt for the peanut butter sandwich, you verify the receipt that sourdough bread is vegan, and then together, once you've proven an assumption as valid, it is no longer an assumption. It has been proven to be true, and so you can actually remove it from the assumptions list. So on the left here, you see you start with two assumptions. You present a receipt for the first one, and then you get to remove that assumption from the list. There's still one assumption in the assumptions list, and so the verifier still can't be sure whether or not a peanut butter sandwich is vegan. So we need to do one more step, which is we need to resolve the second assumption. So we take the conditional receipt, this time with one assumption. We present a receipt that proves that one assumption, that peanut butter is vegan. And then we get to remove that assumption from the list. And now we have an empty assumptions list. So now we have an unconditional receipt that shows that a peanut butter sandwich is indeed vegan. And the verifier will accept this receipt. So let's go deeper into exactly how this works. So we mentioned this resolve step before, and on each resolve step, we need to verify that the assumption receipt is valid. Basically, we have proven the assumption to be true, and we need to verify that the conditional receipt is valid. That basically that the statement with the assumption is itself a valid statement to that statement. And so we need to verify 2 receipts, and we'd like to produce a single receipt. This means that we need some kind of recursion. So basically, what recursion is basically verifying a proof within your ZK VM system. So basically, the ZK, and one way to think about this is that the ZK VM is a general purpose computer. And so the easiest way to make this happen, and this does indeed work, is to send the receipt as input to the ZK VM. You can then run that verification procedure, which is written in Rust, inside the ZK VM. And as a result, you will get a receipt that includes verification of the receipt that was passed as input. Therefore, basically, if you verify 2 receipts inside the ZK VM, you'll have one receipt. Although that basically that attests to the correctness of both of those, at least intuitively. In practice, this is not quite efficient enough. The resulting receipt that we get out is larger than the 2 original 3 receipts. So we want this like 2-to-1 compression. Basically, we take 2 receipts and get 1 receipt. But with this method, using just the verification procedure written in Rust and running in the ZK VM, the result is not small enough. So in order to solve this, we built a recursion virtual machine. And you might at this point go, a recursion virtual machine, what is this? And I'll explain what it is, but first some motivation. So we talked about before, our first attempt at verifying the receipt in the ZK VM was not efficient enough. Some intuition for why this is. Our ZK VM is built on general purpose computing architecture. That architecture is RISC-V. RISC-V is similar to ARM, x86. Basically, these are the architectures for the CPUs that are in our phones, in our computers, and RISC-V is very, very similar to those. It's very good at things that computers typically do. It's very good at 32-bit wrapping arithmetic, bit operations, branches, loops, memory reading and writing. It is not optimized for prime field arithmetic or programs that don't have control flow. Stark verification, being a cryptographic algorithm, is built on top of prime field arithmetic. That's the core of it. And so there's kind of this mismatch here, where what RISC-V is good at is not what we need to do really efficient Stark verification. So as a result, we built a purpose-built instruction set for cryptographic protocols. So the operations included are prime field arithmetic, reading from an input tape, which is a much simpler form of output than we support in the RISC-V ZK VM and the ZK VM that most people will end up using. And it supports SHA-256 and Poseidon hash functions natively. There is no control flow, and the memory is what we call write once, which basically means instead of being arbitrarily readable and writable, every location of memory can only be written to once, one time, and from that point on, the memory is constant. This is much more efficient for using for Stark verification. And as a result, you can actually verify 2 receipts and only generate 1 out. So now we actually do have this 2-to-1 compression. So the Recursion VM runs programs much like the ZK VM. These programs are a little bit different. They don't have control flow. They don't, like I mentioned before, they basically are in some ways simpler. But basically we can't really write Rust and then compile it down to the instruction set that this Recursion VM runs. So as a result, we use our own custom language called Zergen. We also use Zergen for writing our circuits. So basically the Recursion VM itself and the RISC-V ZK VM are both written in Zurgen. And we also use Zurgen to write our recursion programs. Currently, we have 4 recursion programs implemented. So we have a program called Lift, which takes a risc-v receipt and verifies it, which gives you a smaller recursion start receipt. So basically, this is the first step to basically converting from the output, the receipt format of the risc-v ZK VM, and then converting it into the receipt format of the recursion VM. From this point, we can then run programs like join. So the join program takes 2 receipts as input, both receipts being part of the same continuation or continuous execution, and then verifies them both and gives you a single receipt out. And this right here is kind of the backbone of the continuation system. So we have another study club on continuations if you're interested in diving deeper on that. But essentially, this is a system by which we're able to support unbounded length computations. And the way this and give you a single receipt out is kind of the key here. And the way that we do this is basically we continuously take 2 receipts, compress them into 1, take 2 more, compress them into 1. And basically, you can take this, you basically can form a binary tree that covers the entire execution and eventually compress it all the way, take any number of receipts for a continuous execution and compress it all the way into 1 receipt. And this is what we refer to as continuations. And the join program, it has been underlying it the whole time. We also now have the resolve program. The resolve program does what we mentioned before. So go back to this slide here, where you take a conditional receipt and you take an assumption receipt. You verify those 2 receipts and you produce 1 receipt out. That is the same statement, but with 1 condition, 1 assumption removed. So this resolve program now forms the backbone of our composition system, allowing you to get a single receipt for any composite statement, any statement that has assumptions, any statement basically that uses the inf verify call within it for that modularity, for the privacy protection, all the benefits we mentioned before. That is all underpinned by the resolve program. We also have an additional program, which is the identity program. It verifies a recursion start and produces a recursion start. This might seem dubiously worthwhile at first, or not necessarily worthwhile at first, but it is actually used within our start to start pipeline, which is how we take a start receipt and then compress it into a Graf 16 receipt. We actually, when we run this identity program in practice, we actually use it to change the proof system parameters to go from using a Poseidon hash over a 31-bit prime field to a Poseidon hash over a 254-bit prime field, which works very well for the BN254 curve, which is used in Ethereum's Graf 16 verifier. So as a whole, basically, this identity predicate, it's very simple. On the face of it, it just goes from, it basically just verifies a start and produces a single start. But it's very useful for us as part of our start to start pipeline. And in addition to continuations and composition, the recursion VM is something we also intend to use in the future to integrate other proof systems to do more efficient receipt verification and in general, basically allow us to very efficiently integrate cryptographic operations into the ZK VM system. We're very excited about the potential opportunity of this, and you'll be seeing a lot more use cases for the recursion VM going forward. But all of that is a topic for another study club. So back to the big picture real quick. We are excited that composition is now released. We are excited for the next generation applications that use it. We're looking forward to privacy preserving computation, proof aggregation, and modular ZK VM programs. Yeah, and thanks for coming. Definitely feel free to ask any more questions.
Hey, Victor, I have a maybe not necessarily a question, but a comment. When you were Well, when we're composing proofs using composition, um, what there seems to be, there is an element that the programmer has to get correct in that they have to be committing to the correct journal output, right? And so if they don't properly do this, then your assumptions become, how do you say this, like more like the resulting receipt after you do all the resolutions become more like malleable, right? Like let's say that like we have the is vegan kind of program, but we don't write anything to the output, let's just say, to the journal. Then when we aggregate the proof, it means that, oh, hey, we just had a bunch of proofs that say they're like vegan ingredients, but we don't exactly know what is being committed to. Therefore, we don't actually know what the ingredients were. So that's like an essential step, right? Or
Yeah, absolutely. I definitely it's part of like writing ZK VM programs in general, right? It's like you need to make sure you commit to the right things, um, such that uh, that the statement basically is well contextualized, right? So
Mhm.
basically, if you don't, like you were saying before, like if you don't actually say what ingredients you verified, or have some other way of basically committing to this, then the proof obviously doesn't really have much meaning because it could apply to any number of contexts.
Right.
Yeah, so I definitely need to bind the context.
Cool. Um, yeah, thanks for presenting. And I think we can probably wrap this up and put the recording online.
Nice.